Well, thanks for the invitation. It's actually really great to be here. I don't think I've ever actually given a, like a long talk, my research talk at Seoul National University before. I gave a like the short talk at some point at the math department. So today I'm going to actually talk about learning to find evidence, which may sound a bit different from what I usually talk about because I prepared the whole slide set, especially for this talk. I really need to learn about how to reuse the set of slides over and over. But let me see, if I can actually talk about this new stuff, as well as I could with the other stuffs. So if I think about it, so when we think about the evidence means a lot of things. But when I say evidence, I want to talk about what are the things that a neural network or the artificial intelligence system takes as input, and then considers as the subset of the features that support this decision. And it has been known over the past many years, that the evidence visualization really helps. So Ziller and Fergus, Matt Ziller and Rob Fergus from NYU in 2014 pointed out that by visualizing the evidence that is being used by a deep convolutional neural network, they were able to build, or they were able to construct a better deep convolutional neural network that won the ImageNet challenge in 2015. And then detecting the evidence also helped, because evidence by itself tells us a lot about what are going wrong with deep neural networks. For instance, Guranga et al. In 2018 demonstrated that by visualizing or detecting the evidence used by a classifier for natural language inference, they actually figured out that such a classifier is often incomplete, in that it only tends to capture the annotation artifacts rather than the actual phenomena that gives a rise to the inference or the natural language inference annotations or the labels. And furthermore, at the end of the day, we want to deploy all these deep neural networks or the artificial intelligence systems. And then what we want is that what we observe or what we see is that the people who use these deep neural networks want to not only see the decision or the answer from these deep neural networks, but also the evidence. So I was having a casual chat with Hao Dome, who is a professor at University of Maryland, earlier about some websites written in Korean. And then Hao wanted to check whether he could order some items to be delivered to his apartment from this Korean website. And he wanted to see whether his apartment or the zip code was covered in the delivery area. So he asked me this question. So I went to this website. Of course, I could read it. And then I figured out that yes, indeed, the house apartment or his zip code is included in the delivery area. Now, if we are building a simple neural network or the deep neural net-based question answering system, then what we will see is that this deep neural net is going to give us just the answer, that it's yes or no. On the other hand, what I did almost without thinking was to provide some evidence that supports the answer that I provided him, that is the yes. So this zip code is included, and here's the evidence. And then there is a screenshot of the evidence. So people want evidence. So at the end of the day, what we want is that we want to build an amazing artificial intelligence or the deep neural networks, but also at the same time, we want it to be able to tell us what were the subset of the features or the evidence that it has used in order to provide this conclusion or the answer. So in the case, but of course, it's a very, very difficult topic. The explainability or how to explain the decision process taken by humans or AIs, it really doesn't matter, is a very difficult problem on its own. So we're going to narrow it down quite a bit today. And then in particular, in the first part of my talk, I'm going to talk about how to find evidence in the problem of classification, where the problem is simply to build a neural net that's going to take as the input a feature vector or an image or whatever you want. And then this model is going to tell you to which class the input belongs. And then in this setup, we can actually start with a very naive definition of evidence. In this naive definition, evidence is a subset of the input features that influence the classification decision. And then we're not even going to narrow down ourselves to a deep neural networks here. In fact, we're going to think that this is the naive definition of the evidence that we're going to use for any kind of decision-making machine, including humans. So in the case of the, let's say, cat or dog classifier that I showed you on the right side of the slide, the face of the dog or the paw of a dog is going to be considered an evidence because that's a subset of the pixels that the classifier or yourself could look at and then make a decision whether this image belongs to the category of cat or dog. On the other hand, any pixels that belong to the background or any pixels that belongs to the torso of the dog are not going to be considered as evidence. Makes sense, right? Okay. Now, let's see. So then, we need to now think about a bit further in order to detect all this evidence, what it means, or what are the consequences of this definition of the evidence. First, we notice is that if the evidence, this subset of the features, is removed, then predictive distribution must change. Because all those features that were influencing the classifier's decision were removed, the classifier, of course, cannot make the same decision any further. However, when non-evidence, that is a subset of features that do not influence the decision of the classifier, when this non-evidence is removed, the predictive distribution stays same. So as an example, this is a prayer dog or something like that. But then when the dog itself is removed from, oh, actually it's a meerkat. I'm sorry about that. When the meerkat is removed, then classifier's decision must change, for instance, to the field. On the other hand, if the non-evidence, that is the background other than the meerkat, is removed, then classifier should ideally output the same kind of prediction because the entire evidence or the subset of features that influence the classifier's decision remain same. So then now we can think about trying to make an algorithm that's going to detect this evidence automatically. To do so, I'm going to introduce some of the notations, but the math in this talk is going to be pretty minimal, so don't worry about it. So we're going to have an input, which is going to be a d-dimensional vector. You can think of an image, which is a two-dimensional vector or the three-dimensional tensor, as a very elongated vector, so don't worry about it. And then what we want is to find a set of pixels or the set of features in this image that are going to influence the classifier's decision most, and then how we are going to indicate whether each pixel is evidence or not is by introducing a mask. And then in this case, mask is going to take for each pixel the value between 0 and 1. And of course, we have a classifier, which could be a deep neural net, but it doesn't really have to be deep neural net as well. We could have used any classifier of your choice. And we have a scorer or the loss function, which I'm going to talk about a bit later, that's going to tell us what was the actual output of this classifier and then what the decision of this classifier was. Then the problem of finding an evidence mask corresponds to or becomes the problem of maximizing this loss or the score with respect to the ground truth label when it's applied to the input while minimizing the evidence area. So what does that mean? So what we're going to do is we're going to take the evidence mask, which is supposed to tell us which pixels are evidence. I'm going to invert it. So thereby this mask is now going to tell us what are the non-evidence area. And then I'm going to now get the image, multiply with this non-evidence mask, and then I fit that into my classifier F. And then I'm going to look at whether this classifier is going to give a good probability or the high probability to ground truth. And then what I want is that because the actual evidence has disappeared because of the masking operation, we want this classifier not to put high probability on the ground truth label. And then that is to maximize the negative low probability of the correct label given this input without any evidence. Now, of course, this problem can be solved trivially. The reason being that if you simply say that every pixel feature is evidence, and then you're going to remove every pixel from the input. And of course, this classifier won't be able to put any high probability to the ground truth label. So that's why we want to put a regularization term. There's a second term in the equation at the center that tries to minimize the area occupied by the evidence. So in this particular case, you can think about counting the number of the non-zero pixels, which would correspond to trying to minimize the L0 norm, but L0 norm is a bit difficult to minimize. So we're going to simply use the L1 norm of the mask. So once we solve this problem, then this evidence, this mask is going to try to find a subset of pixels or the subset of the features that are going to act as evidence for this particular classifier. And this is the way that has been studied by a lot and a lot of people. I have just listed some of them at the bottom of this presentation slide, but there are even more. Of course, it makes sense. And then if you apply this to, let's say, ImageNet classifier, then you do see that it kind of works well, right? So this is a particular set of examples that were selected from the class birds in ImageNet. And then what you see is that on the top row, we have the original input, and then second row is the visualization of, or the masking out of the non-evidence. And then you do see that the most of the remaining pixels do correspond to birds. So it looks to be working pretty fine. Makes sense, right? However, if you look into each of these examples more carefully, then there are some issues or the immediate issues that you can notice right away. For instance, you do notice that this classifier, in fact, has captured the spurious correlation between the existence of a tree and the bird class. And this should not be the case. The existence of the tree should not be an evidence that the image should belong to birds. However, because the data set, we have only a finite amount of the data set, and then there is some kind of systematic bias that the most of the birds pictures were taken in the forest or while birds are sitting on the trees, this classifier has captured that kind of spurious correlation. So that's not desirable. And then second thing is that the features or these pixels are extremely correlated. And then what happens is that this classifier is going to rely only on a subset of these features that define birds. The reason being, all these pixels are correlated. There's no need for the classifier to look at the entire set of pixels that define a bird. All it needs to look at is the minimal subset of this subset of the pixels, because it can figure out what other pixels are going to be relatively easily. So these are not really a desirable property. And then now at this point, you need to start wondering, does this make sense for us to think about an individual classifier and then trying to extract the evidence for this particular classifier? And then, in order to make move forward or away from this classifier-dependent evidence extraction, we need to think about what is the cause behind this kind of undesirable behavior. And then that can be very succinctly described as the correlated informative features. So correlated features are the features that I just told you about, is that many of the features co-occur in the naturally occurring, let's say, data set or the examples. And then the neural nets just cannot distinguish those two. So it cannot tell that whether it is the actual bird that should give a rise to the conclusion or the decision that the input should belong to the bird, or whether it's a forest that should give a rise to the class bird. And also there is the issue with the informative features, that the input features are predictive of the classes, but there are many different such features within a single input that are mutually correlated. So any appearance feature of a bird is going to be informative. It doesn't have to be entire bird, the appearance of the entire bird that matters. And then there comes a really interesting connection between this inability or the undesirable behavior of the dim neural nets when it comes to trying to detect what kind of objects are there, with the fact that the objective function we're trying to minimize or maximize in order to train this dim neural net is non-convex. So you may have heard about, or that you may know actually more better than I do, that the objective function or the loss function for training a neural net is non-convex, meaning that there are going to be many possible minima or the saddle points that are going to hinder our learning, which is often based on the stochastic gradient descent. But once you start thinking about it, you suddenly start thinking about, okay, so if there are many such solutions, many such minima in this non-convex objective function, what does each of those minima correspond to? Are they all equally good? Are they all equally bad? Do neural nets that correspond to different minima, do they behave similarly with each other? Do they behave the same? Or do they behave differently? It turned out that they all do behave more or less differently. And then this cannot easily be detected by simply looking at the validation or a standard test set accuracy. All those minima are going to often correspond to more or less the same level of tested accuracy or the generalization accuracy. However, when you're trying to do the fine-grained analysis of their behavior, then you do notice that each and every one of them behaves in a very distinct way, making them very different from each other. And then it's not really surprising, in a sense, if you started thinking about it from the Bayesian inference. So if you think that these neural net parameters are all just random variables, and then we're trying to estimate the distribution over these random variables, there is the parameters given the data, then this non-convexity of the objective function effectively tells us in this Bayesian way that this posterior distribution is highly multimodal. So there are many possible peaks in this posterior distribution. And then what the Bayesian approach tells us is that we should then consider all of them, because they're going to capture different aspects of this data. And then what we don't want to do is to simply pick one of them and then rely on that classifier, but rather we want to consider as many of those picks as possible and then average the decisions from them. And then that's how we ended up with so-called classifier-agnostic evidence detection, or the saliency map extraction. So instead of trying to consider a single classifier, which has its own idiosyncrasy in terms of what it takes as the evidence in the input, we are going to try to consider all possible reasonable classifiers that we get from all those minima in this objective function, or all those picks in the posterior distribution. And then we're trying to extract this mask, this evidence mask, that's going to leave out all this non-evidence part by multiplying the input with a 1 minus m, and that's so that on average, all the reasonable classifiers are going to change its decision. So it's a bit of a kind of the same confusing thing, I can understand. Yeah, it took us some time to actually formulate this in 2017 and 18. So the idea is that there are so many possible neural nets that seemingly perform at the similar level when it comes to standard tests that you're going to create. However, when you look at individual neural network more carefully, then you notice that each and every one of those neural net behaves differently from each other. And then what we want is that we want to consider all those neural nets and then trying to extract an evidence that's going to be used by all of them instead of just taking one of them. And at this point, many of you might realize that, yeah, wait, hold on, does it actually make sense, right? Is it possible to even solve this problem? Because the posterior distribution over this gigantic neural nets is going to be extremely complicated, and it's very clear that computing this expectation is not going to be tractable. So we're going to talk about that shortly after talking about some of the the side steps, some of the the quick changes that we made. First thing is that we were initially a lot of people have been thinking about, okay, so we need to be able to find the evidence mask so that the non-evidence, so classifier given the non-evidence part only is going to assign as little probability to the correct class as possible. But then you raise a question, is that what we really want? In fact, if you think about it just one step further, you notice that the lack of evidence should not change the actual probability or change the decision of the classifier at all. In fact, the lack of evidence should maximize the uncertainty of the classifier. So if the evidence is not given and only the non-evidence is given, this classifier should not be able to tell what which class to which the input belongs. That is, if you think about the cat versus dog classification, the example from earlier, if the input lacks either cat nor dog, then this classifier shouldn't say whether the input is cat or dog. It should simply say that the chance of this image being cat or dog is half. Essentially, it doesn't know anything, and then its uncertainty is maximized. So we're going to replace this score function from the loss function to the entropy. So we want to maximize the entropy of the output class or the conditional distribution of the input. And then the second tutor is the amortization. So I've been talking about as if we are having a single mask that we're going to extract by solving this optimization problem for each and every input. However, it's a bit too expensive, right? All these neural nets are gigantic, and especially if you want to do the marginalization over all possible neural nets for this classifier independent or the agnostic way, then it just doesn't work work in real life. So what we want is that we want to amortize this cost of optimization into learning another neural net that's going to take as the input the original input or the image, and then outputs the entire mask at once. So then thereby the cost of extracting this evidence is not going to be it's not going to be proportional to the amount of time you need to solve this optimization problem, but more like it's going to be a constant time in the test time. And in other words, we're going to simply learn another neural net that's going to extract the evidence mask for us, given the image. And now let's get back to the issue of the difficulty or the intractability of solving this posterior inference problem. So what we're going to rely on is the idea of using stochastic gradient descent in order to solve the problem of the posterior inference. It has already been known for quite some time. Already in 2003, McKay's book in the information theory, it was mentioned that it is a good idea to use the information of the gradient if you have access to the gradient information of the posterior distribution. And then it turned out that we actually do have access to the gradient information of the posterior distribution because we do have the gradient of the loss function. And then Welling and Tay in 2011, as well as the Mans et al. In 2017, showed that by using SGD and then adding some noise, the samples we get, or all those intermediate iterates we get from the optimization procedure, are going to form a set of samples from this posterior distribution. So all we need to do is we don't need to solve the expectation problem exactly, but all we need to do is we solve the problem of the minimization, that is to train this classifier. And as long as we add some noise, it's going to in fact give us all those samples from this complicated posterior distribution. So then we end up with this algorithm. We call it classifier-agnostic evidence detection, or the salience map extraction, where we have two stages. First stage, and then we alternate between these two stages. First stage is the sampling stage, where we sample a one point from the classification posterior distribution. So we're going to update this classifier F just a little, following the gradient we compute from the loss function, however, with some noise. And then in the second stage, given this new sample F prime, which is going to be a randomly drawn sample from a set of classifier samples that we collect in the first stage, we're going to take one of them randomly, and then we're going to update the evidence mask network in order to maximize the entropy of the predictive distribution of this classifier F prime. And then we're going to alternate between these two stages until things converge more or less so. Of course, this convergence is really difficult to tell because if you have noticed, the objective function is not really well defined in this case. So we are sampling from this posterior distribution with the noise, while we're trying to maximize the entropy of the evidence mask, where this entropy in fact depends on the optimization procedure we use in order to sample from this posterior distribution. So it's a pretty complicated, let's say, two optimization problems that we want to solve when these problems are interdependent on each other. However, it turned out that as long as we start from a reasonable initialization of the classifier F and the reasonable initialization of the evidence mask network, this procedure generally works quite well. So this is what you would get if you're trying to extract the evidence from a single classifier that was really well trained on ImageNet. Now, if you move into this classifier-agnostic evidence methods, then what you do see that the evidence looks so much better. So evidence now does consist of almost all the feature or the evidence pixels that correspond to the entire object, while non-evidence indeed does consist of all those background pixels. If we go into a bit further, first observation we make is that indeed is the full object that is detected as evidence, and the background is considered non-evidence. Now, second observation, which is more interesting in my opinion, is that a lot of the spurious correlations that were captured by a single classifier and were detected as the evidence when we considered only a single classifier are not considered as evidence anymore. It is not perfect, of course. It's just impossible that this kind of statistical analysis will remove all the non-causal spurious correlations of the evidence. However, what this Bayesian inference allows us to do, or that saves us, is this issue of the correlation, this issue of detecting a, let's say, extremely spurious correlations. So one of those many classifiers or the minima may correspond to detecting a spurious correlation, but because we're considering all of them, unless that feature is important or influences majority of all these classifiers, that those features are not going to be considered as evidence, which is the strength of the Bayesian inference. Although, again, this does not really save us from the core issue of the correlation versus causation, which I'm going to talk about briefly in a few slides, I think. So this was the first part that I wanted to talk about, is that when we think about the evidence that is being used by an AI system or the deep neural network, it's actually not as simple as we may imagine what evidence is. Evidence may mean that it is the subset of features that are used by a specific classifier to solve a problem. But at the end of the day, this can be very misleading, because as soon as you train another classifier on the very same data set, you may actually end up with a classifier that looks at different subset of pixels to solve the same problem. And then you won't be able to tell the difference between these two just by looking at the test set accuracy. So what we looked at was that we could actually define the evidence slightly differently, and then say that the evidence is the one that is going to be used by any classifier to solve a problem. And then to do so, we demonstrated by creating an algorithm that is based on the Bayesian inference to find this evidence that's going to work for majority of the classifiers. And then it turned out that this classifier-agnostic evidence detection addresses the issue of the correlated features, and as well as the issue of the informative features, up to some degree. Is there any questions before we move on to the second part? I can look at the chat window, or if you have any questions, you can of course just talk, speak up, of course. No, I guess not. Well, my talk seemed to be very clear. No question. Oh, okay. So there's yeah. If there's no question, of course. Oh, you cannot turn on the microphone. I mean, can you just type on the chat window then? I can read it. So. But otherwise, I mean, okay. Few questions. Okay. So Ernest Ryu, you have a few questions. I think you can actually turn on your microphone and ask a question yourself, in fact.
네, 안녕하세요. 그 질문이 몇 가지 있는데요.
네.
그 에비던스를 보여주는 그러니까 네, 여기서 네 번째 로는
예. 그 네 번째 로 같은 경우는 에비던스 픽셀들을 뺀 후에 그다음에 이미지 인 페인팅을 한 겁니다.
네.
그래서 그렇게 한 이유가 지금 이 슬라이드에서 왼쪽을 보면은 베이스라인 어프로치, 이제 클래시파이어 하나만 한 경우에는 에비던스 픽셀 빼고 인페인팅을 하면은 전반적인 쉐입이 다시 살아나고요. 그에 비해서 클래시파이어 애그노스틱한 어프로치를 하면은 아예 쉐입 자체가 사라지는 걸 확인할 수가 있죠.
네, 알겠습니다. 또 질문이 있는데요. 이제 실제로 뉴럴 네트워크 어떤 클래시피케이션이나 어떤 뭐 그런 것에 이제 디플로이를 한다라고 생각을 했을 때 원 싱글 뉴럴 네트워크를 이제 디플로이를 할 것 같다는 생각이 들거든요. 실제로 회사 컴퍼니들이 어떻게 하는지 저는 잘 모르지만, 그렇다라고 한다면은 그 싱글 뉴럴 네트워크가 결국 사용하는 에비던스는 이 클래시파이어 애그노스틱하지 않잖아요. 그러면은 그런 상황에서 이렇게 클래시파이어 애그노스틱한 그 에비던스를 이제 뭐 이렇게 러닝을 했을 때 이걸 어떻게 커넥트할 수 있을까요? 프랙티컬하게.
네, 맞습니다. 그 에비던스 이제 디파인을 어떻게 하냐에 따라 다른데, 실제로 이제 서비스를 디플로이해서 쓸 때는 보통 클래시파이어 1개 아니면 많이 해봤자 한 2개 정도만 하니까 에비던스는 당연히 클래시파이어를 맞춰가는 거를 보고 싶어 하겠죠. 그래서 이제 클래시파이어 이런 애그노스틱한 방법으로 에비던스를 찾을 때 이걸 어떻게 사용하냐는 아직 굉장히 오픈 퀘션입니다. 근데 아마 파트 2에서 제가 조금 보여드릴 수 있을 것 같습니다. 어떤 식으로 활용할 수 있는지. 네.
네, 알겠습니다. 마지막 질문 하나 더 있는데요. 아까 amortization 사이드 노트에서 이제
네.
그 마스크를 separate 뉴럴 네트워크로 트레이닝한다고 말씀하셨는데 이거를 그러니까 말씀만 그렇게 하셨던 걸 수도 있지만 이걸 클래시파이어랑 이제 마스크를 이제 하나의 뉴럴 네트워크로 트레이닝을 해서 두 개의 아웃풋을 내는 하나의 뉴럴 네트워크로 트레이닝하는 게 조금 더 이피션트하지 않을까 하는 생각이 드는데 이거를 두 개를 완전 따로 트레이닝하는 게 더 in practice 낫나요?
아니요, 사실 저희는 따로 트레이닝은 했고요. 이제 인풋 두 번째 그 마스크 네트워크의 인풋으로 사실 first layer에 있는 모든 피처 맵을 다 넣어주긴 했습니다. 그랬더니 좀 더 트레이닝이 빨리 됐던 거는 확인을 했고요. 근데 실제로 이거를 좀 효율성을 생각을 하면은 당연히 저 같아도 마스크 네트워크랑 클래시파이어 네트워크를 궁극적으로 합쳐서 끝에 두 개의 헤드만 따로 만들 것 같습니다.
네, 감사합니다.
예,
네, 어네스트 류 교수님이 그 수학과 교수님이셔서 이 처음 보는 수식도 이렇게 빨리 팔로우를 하시는 것 같습니다.
설명을 잘
질문
주셔서.
김관 교수님 말씀하시죠.
예, 저도 질문이 있는데, by the way, is there anyone having difficulty understanding Korean? Then I will ask questions in English, otherwise in Korean.
I'm fine with
English
either.
would be better.
What? Which way is better? You said.
English is better.
Okay, then I'll ask in English. Thank you for a very interesting talk. I think the key issues are somewhat related with the concepts discussed much in statistics, econometrics, and neural network. Those concepts are variable selection, filter selection in your otherwise, in other words, evidence selection, and then regularization concept appears, and model averaging and Bayesian inference are also parts of your analysis. Also, you mentioned the relationship between correlation and causation.
Yes.
I think all these concepts should be used for certain objectives in mind. For example, if we're interested in just prediction, then maybe some people would not worry much about distinguishing between correlation and causation. In the example of bird and branches of a tree, sometimes it helps to have branch of a tree to predict the object is a bird. In that case, even though the relationship between branch and birds has nothing to do with causation, such correlation might help if your purpose is in prediction. So depending on the clear objective, sometimes certain concepts we need. In other cases, if our interest is in pure causation, then obviously we want to rule out correlation. So how do you think about that?
I definitely agree with you in the sense that whether it is always desirable to build a neural net or any kind of, let's say, classifier that uses only the causal features, I think we don't really know the answer to that, because what that does is that it actually restricts a lot of things that we can do. So if the goal is to build simply let's say the best predictor with the average generalization accuracy, there's absolutely no reason why we want to stick to the causal features only. In fact, most of the correlational features are going to be useful, or in fact more useful. However, there are a lot of the mission critical applications where the causality actually matters a lot. And then I'm going to actually talk about that briefly at the very end of my talk. It's only halfway, so I gotta speed it up a bit. I'll be able to answer that. Yeah, and then there is one question on the comment box that is that 혹시 액티베이션 맵 어프로치랑 비교했을 때 결과에서 큰 차이나 효율 면에서 차이가 있을까요? 효율 면에서는 뭐 여기는 당연히 뉴럴넷이 하나가 더 있고, 그리고 그 뉴럴넷을 트레이닝을 시키기 위해서 여러 뉴럴넷을 생각을 하는 이제 그런 베이지안 인퍼런스까지 해야 되기 때문에 효율 면에서 굉장히 떨어지고요. 하지만 실제로 이 결과, 이 에비던스, 뭐 어떤 클래시파이어 타입에 상관없이 어떤 에비던스가 이러한 딥러닝 기법에서 사용이 되는지를 찾기 위해서는 이 방법밖에 없습니다. 그러니까 사실 활용도 자체가 아예 다르다고 보는 게 맞는 거죠. 그리고 이제 뭐 두 번째 파트로 넘어가겠습니다. 아무래도 시간도 별로 없고 최대한 빨리 가야겠네요. So we now know how to extract evidence that is used by a deep neural networks. whether like it's for a very particular classifier or the deep neural net, or whether it's a family of the deep neural nets that's going to be trained on the same data set, but starting from the different, let's say, initialization. But then now there is another big question that we want to answer, is that does that evidence generalize to us or to other neural networks? And then in fact, if I abstract it out a bit further, then the question is, okay, do neural nets behave like us? In 2013 or 14, actually in 2013, iClear, I was there in Scottsdale. And then one of the talk was given by the Caduel, on demonstrating the similarity between the activations from these deep convolutional neural nets that were trained on the ImageNet and the measurements of the brain activities from monkeys or the macaques. And then there was an amazing presentation. And then it showed that those two sets of activations, so one from the biological brain and then one from the artificial brain, the fact that they correlated with each other that highly was just very shocking. And then I think that that's when people started to seriously ask whether these artificial neural nets that we built and then that we have been able to scale up with a large amount of data, in fact, do behave like us. One thing you have noticed probably from the first part of my talk is that, of course, they don't. So you build the ImageNet classifier. This classifier is supposed to be able to detect all those birds amazingly well, except that what we have seen is that these classifiers are going to look at branches of a forest to tell that there's a bird or not. And then no human is going to do that, right? Unless the birds are not visible. We're not going to use the branches to tell whether there's a bird or not. So the answer is clearly no. However, what we want to ask is more like, what is the degree to which neural nets evidence transfer to other neural nets, including humans? Because it's going to be more like the spectrum rather than binary dichotomy between yes or no. So in this part, I'm going to talk about the reading comprehension. I'm going to go into the natural language in this case. So there are a number of reasons I'm going to talk about, but in reading comprehension, I think almost everyone in Korea knows about it because we've been studying for TOEFL, and then some of you may have studied for the GRE and so on. So we're going to be given a paragraph or the passage, and then we're going to have a question. And based on this passage and the question, we need to find one of the 4 or 5 candidate answers. We need to select from one of the 4 candidate answers. So if we, in this particular example, if we had read the whole passage, and then if you looked at the question, in the US, taxes are collected to provide revenues for, then we'll be able to easily answer after some time that the answer is D, the 3 levels of government. However, the interesting thing is that if I had taken only a single sentence from this passage, for instance, the single sentence that is the federal government has 2-level income tax that is 15 or 28%, and then ask you the same question that in the United States, taxes are collected to provide revenues for, then you would actually answer that the answer is A, the federal government. In fact, I can do that for the second candidate answer, the state government, as well as the third candidate answer, the city government. So what it means is that the reading comprehension is really interesting in a sense that it does allow us to study the evidence that is being used by neural net as well as humans. And then we have a huge amount of, or the gigantic level of controllability. Because each paragraph or the passage often has evidence supporting each and every candidate answer. And then in the reading comprehension, often the questions were created to confuse the test takers. So the candidate answers, all of them are often very easily defendable if you only look at a small subset of the passage. And then the evidence is often complete. If you look at the evidence in an image, after leaving out all those non-evidence, you see that something is weird. It doesn't look natural at all. However, in the case of the text, if I only take 1 or 2 sentences from the passage as the evidence sentences, then that sentence or the evidence text is going to look like a complete text. So this is pretty nice. So we're going to work with the reading comprehension. So in the case of the evidence detection in reading comprehension, we're given a question, we're given a paragraph, we're going to consider paragraph as a sequence of sentences. And then we're given n many, so few answer candidates, which is going to be considered as a set of answer candidates. And then we're going to assume that we are given a judge. So judge, is just a term that we created. So it's a classifier. This classifier is going to look at the question and the paragraph along with the answer candidates, all of them, and then it's going to give us a distribution over the answer candidates. And then you should put high probability to the correct answer. Now then, the evidence detection and reading comprehension becomes trying to find a subset of the sentences in this passage that's going to maximize the judge's probability assigned to the target answer candidate. So now we are trying to find the subset of the sentences that are going to make the judge or to convince the judge to think that the answer to this given question Q is the target answer A. Unfortunately, it's a very difficult problem to solve. There are often the passages consist of the 10s, if not 30s, or the 40 sentences. And then there are just, exponentially many possible subsets that we won't have time enough to consider all of them. So we can think about two different ways to do so, two different approximate ways to do so. One is to do the greedy search or some kind of, let's say, variance of that. That is, we're going to say that, we won't be able to consider all possible subsets or the power set of the sentence set of the passage. So we're going to simply pick one sentence at a time for each and every candidate answer up to the constraint. So we're going to put some kind of constraint, just like we put the regularization or we impose some kind of soft constraint earlier on the size of the evidence mass. We consider the multiple different ways, but the details actually do not matter that much in this case. But you can just consider that it's not that difficult to come up with some heuristics that works reasonably well. I'm going to show you what I mean by it works reasonably well. The other direction is just like the amortization from the classifier-agnostic evidence detection earlier, is that we're going to train another neural net that's going to look at the evidence sentences, all the evidence sentences, and then the question as well as the target answer, and then trying to see how the judge's answer or the distribution changes. And then we try to predict it for each and every evidence and the sentences in the passage, every sentence in the passage. And then we define certain type of the criteria in the test time in order to select only the top K evidence sentences that are going to be selected by this predictor. Unfortunately, I don't have time to go into the details, but if you're interested in it, this paper is online. So you're welcome to look at it. If you have any questions, just shoot me an email. So now what we want to check is that whether this kind of evidence that is going to be extracted from one of the neural net is going to be transferable to another neural net as well as humans. So we need to have a set of families of the classifiers that are able to solve this reading comprehension problem. So we built a bunch of, let's say, reading comprehension models. We built the unsupervised model that's going to rely on the TF-IDF vector. So it's going to look at just a word overlap between the question and answers, or the question, answers, and sentences. And then second one is the unsupervised fast text judge. Is very similar to the unsupervised TF-IDF, except that we're going to use a dense vector based on the fast text or the word-to-vec algorithm. And of course, we have a supervised model that is explicitly trained to solve this kind of reading comprehension model. And we actually did the experiments with the human volunteers or the mechanical Turkers as well. So let's look at how well these judges solve the problems or the reading comprehension problems. We consider two different data sets. One is called RACE, the other is a DREAM. Both of them are reading comprehension problems that were created for the, if I remember correctly, Chinese students, mostly either in the high schools or in the middle schools. And then these are pretty tricky reading comprehension problems. And then what we see is that most of these judges are not doing as well as human adults. Human adults are doing much better. However, we do see that this BERT-based supervised model, in fact, works quite well. Now we're going to see whether this performance on the reading comprehension, in fact, correlates with the transferability of the evidence among all these models. So how do we check the transferability of evidence? So what we're going to do is that we're going to detect the evidence, and then we're going to show only the detected evidence sentence and the question along with the candidate answers to the human or another model, and then ask the model, the target model, to answer this question only based on the evidence. If the human or the target model chooses the target answer, not the correct answer, then that's a success. So what it means is that we now trying to see if we can manipulate or take the subset of the passage in this reading comprehension to convince the test taker that the answer the test taker needs to choose is the answer that I want this test taker to choose. So that's going to tell if that the success rate of that is high, then that means that this evidence is highly transferable. So in order to check the transferability of evidence to humans, we have some baselines. So how often does a human choose the correct or the answer that we want it to if we simply selected the random sentences? Of course, it turned out that it's going to be a quarter of times. So that is because it's just a flat uniform random over the 4 possible candidate answers. On the other hand, the upper bound should be, what if another person look at the question, passage, and one of the target answers, and then selected the evidence sentence? It turned out that the overall 42% of time, the target test taker is going to choose the answer that was used to extract this evidence. So what it means is that the good evidence sentences convince people to choose target answer candidates when what's done with the humans. So let's see if that is the case if we're trying to extract the evidence that was used by the neural network. So there is a lot of bars here, but we're going to look into one at a time. So first thing we notice is that in fact, this evidence does transfer to humans. And the funny thing is, when we try to use the evidence sentences from more accurate models, such as the supervised BERT model, then this transferability is as high as the evidence selected by people themselves. It's quite amusing in a sense that even though the BERT-based model was not solving the problem as well as the humans, but the evidence that the BERT model was using was as meaningful as the actual humans were, the evidence actual humans are using. Furthermore, what we notice is that the amortization actually works really, really well. So because of the amortization, in fact, we can extract this evidence and transfer it to humans in constant time in the test time. So it turned out that this is really a good approach in general, and then these neural nets are really good at trying to learn this, some kind of regularity behind the optimization procedure, allowing us to solve a lot of the optimization problems in constant time. So yeah, I mean, this was a really surprising finding, is that the highly accurate neural nets, which are in fact not as accurate as humans, they use the evidence that is transferable to humans. And then it actually is the whole picture is slightly more complicated than then. When we look at the transferability to humans, that's correct. More accurate, the better. However, the evidence by humans, so evidence selected by humans, transferred better to the models that were less accurate. So this one, we have absolutely no idea. I have no idea why this should happen. I think that we need to give some more thought and then do some follow-up work. But it turned out that there are a lot of interesting structures behind the evidence that is being used by these neural networks. And then whether those evidence can transfer from one to another depends on the family of the networks, learning algorithms that were used, and also their performance with respect to the human performance. And then one thing you notice here is that let's go back to this example, is that if I took only the sentences or only the evidence sentences, so the 4 sentences here, and then put it as the summary, then this passage alone is a great summary for answering this question. So it's a kind of way to build an automatic summary generator from a long passage. And it's going to be very much oriented toward question that is in our mind. So it turned out that this is indeed true. So what we can do is we're going to use BERT to extract the evidence, right? And then, well, not BERT, but any kind of neural net, any kind of judge models we have, we're going to extract the evidence without knowing which one of the answer candidates is the correct one. So we get 4 sentences out of it for each question. We combine them into a one passage and then present it to the test taker with the question, and then see whether the test taker now answered this question as accurately as they would had they looked at the entire original passage. It turned out that it's actually pretty close. So if you use the BERT-based model, which is one of the best performing model here, and if you only show the evidence sentences selected by the BERT-based to humans, then they can answer the question correctly more than 80% of time. And then this is as opposed to about 90% of accuracy the human would get when they had seen the entire passage. So it does actually tell us that the evidence, one of the things in which evidence can be used is to get the good summary of the input. And then it does substantially improve the speed at which humans can answer these questions. And then it turned out that these evidence sentences from the neural nets are as good as those evidence sentences selected by human annotators, which means that we can really use this kind of evidence to significantly improve the efficiency of trying to read or understand the text that is going to be given in the future. So this could be one of the applications of the evidence. So the thing is that I actually promised in my abstract, there were 2 parts. I prepared the 3 parts, but unfortunately I'll have to skip the 3rd part. But let's try to conclude the 2nd part. So it turned out that this kind of evidence that we get from these neural nets nowadays with the very scaled up and high performing neural nets are indeed a good evidence even for humans. So there is this actually does give us a supporting evidence that these neural nets are becoming more and more like human-like. And then it actually allows us to study these neural nets in order to tell even how the human reasoning works. Of course, we are very, very far away from building neural nets are going to work just like humans, but we are seeing the indication that our progress is there. And then we just need to push much forward. And then furthermore, there was an interesting, let's say, observation that the evidence is the summary of the input, and then we can probably use it for various other purposes, one of which is going to be goal-oriented summarization. So since I'm almost done with the talk, I actually have a concluding remark that I'm going to just finish off my talk before I receive any questions from the audience. So this is the 3rd part. This is pretty fun, but I'll share the slides with all of you so that you can take a look at it. So just to conclude my talk in general, first thing is that when we try to interpret the deep neural net's behavior, we have to think about the kind of properties that deep neural nets have. That is that these neural net can consider a different subset of correlated informative features to solve the problem. And then it often helps us to both to solve and to understand these neural nets by considering as many neural nets as possible. And in this particular case, it turned out that Bayesian interpretation does help us do this observation of the many neural networks. Of course, there is a second aspect to that. That is that how do we manipulate this relevant evidence to arrive at a decision, or how do neural nets manipulate this relevant evidence internally to arrive at a decision? But that's a too difficult problem, so I really don't have any answer to that. And the second thing that we talked about was, okay, do deep neural nets behave similar to us? It turned out that up to a certain level, we started to see some convergence of the behaviors of the neural net and humans, and it does present very exciting opportunities. And then the 3rd part, I couldn't talk about it. So these are the exciting conclusions. However, I do have some somber concluding remark, is that what we have seen over the past 5 to 6 years, not only by me or my group, but by the general community that are working on deep nets, is that these deep neural nets are extremely good at capturing spurious correlations that are not causal nor generalizable. And then we saw that by looking at how well these deep neural nets are capturing the fact that the branches or the forest or the green color in the background almost always appears together with the birds. And then in fact, this turned out to be true in general. Many of these image classifiers that we built are trained on image network COCO. And then the image distribution or the distribution of where those images were taken are extremely skewed toward North America and Europe. And as you can see on this screen, you're going to notice that there's almost no image in ImageNet that was taken, for instance, in India or China. On the other, when almost half of the population are in these 2 countries. And then what happens is that these classifiers thereby, it turned out, work better if we give the image that were taken from US or from Europe. And then the classifier accuracy degrades quite significantly if you give the images from other places. And also there is a huge correlation between the accuracy and the income level. And that's precisely not what we want. image classifier should not be, it is susceptible to the income level of the household where the image was taken, picture was taken. But these neural nets are capturing all those weird spurious correlations. And furthermore, these neural nets actually do infer all these unobserved features from the correlated features, and then often make us arrive at a wrong conclusion. So there was a paper from Stanford talking about how the dim nets can detect whether the person is gay or not by just looking at how they look like, which is kind of ridiculous. That's how the Nazis actually, trying to figure out who are actually smarter or not. But it turned out that based on the very nice, let's say, investigative, let's say, work by the people from Google, they show that in fact what this dim neural net does is to figure out whether the images contain people who have makeup on or not, who have the glasses or not, or all those various features that we did not think that neural nets were using. And then by doing so, these neural nets were actually making a decision not based on the actual appearance of the person, but more of the social construct. So these actually do happen, and it's not really a hypothetical scenario that we're talking about. And in fact, recently I had some issue with this, the news article from the Korean newspaper about the so-called AI, interview or job interview. And then what happens is that when these deep neural nets or the machine learning systems do detect all these incorrect, non-causal, non-generalizable conclusions, evidences, then what it does is that it's going to in fact amplify all these incorrect, let's say, biases that society has. And then that can actually negatively impact people and lives at scale. So we should be really careful. And then again, this is not a hypothetical scenario. It turned out that like about 700 companies in Korea are using this AI interviewer software. And I was like, what? No, that's not true. But it turned out that that was indeed the case. So what we need to do is that we need to ensure that the diverse group of people are watching and scrutinizing the development and deployment of the AI systems. As we have seen today, as I have been able to show you, all these evidences of the deep neural nets show us both, let's say, positive and the negative side. Positive side is that they do actually correlate well with the human behavior, the evidence that we think are important. But at the same time, there are certain part of the evidence that is completely, let's say, off the, any kind of common sense. And then we have to be careful, otherwise we're going to make a wrong conclusion that can actually negatively impact a lot of people's lives. So, and to do that, we got to understand the mechanics behind the AI, ML, and statistics to know how these systems operate, and then to be able to intervene. And then, I think just to finish it up, this is a bit of a joke, but I think the Graduate School of Data Science could do better in terms of the invited speakers as well. These are all male, like the speakers from the Silicon Valley or Korea. So I think we can actually invite a more diverse set of speakers. And that actually is the end of my talk. And thanks for listening. And then I apologize for going over time. And if you have any questions, I'll be happy to stay here and answer them. Thank you.
Well, thank you for your inspiring talk. And I think your talk opened our eyes to the very fundamental problem of the AI. Actually, also thank you for your the advice. Actually, in the next semester, we have a list of speakers, and then some of the speakers are female. And, so we are already thinking about that, but this.
I'm very happy to hear that. Yes.
Yeah. Okay. I would appreciate if you recommend the speakers.
Yes.